Okay, it's a pleasure to have Antonio Díaz Ramos from University of Málaga today. And he will be talking about Quillen's conjecture. Okay, thank you, Antonio. You can start.
Okay, so thank you, Sihan. So this is my first seminar talk online, so I hope everything goes fine. If you're not listening to me or something happens, just tell me. I used to do some teaching on this system, but let's see how it goes through. So yeah, thank you for the invitation. So now I am going to miss, because if I were there, I for 30 minutes or something like that, so I'm going to miss that. But you owe me one dinner or something. Yeah. So let me start with this. So I'm going to talk about this Quillen's conjecture. So I'm going to do like in a Blackboard, right? So I will be writing on this table, in this graphic table or whatever, and I hope that you can follow everything here. So let me see. Okay. So what is this Quillen's conjecture? So I need to talk about. So we will start talking about some finite groups. So let's be G finite group, and then P is going to be a prime. So can you see this that I am writing here? Yep. Okay. Thanks.
Yes.
Yes. So this conjecture has like two, like many conjectures. There are two sides. There is the algebraic side, and then there is also the topological side, right? So I need to introduce a few easy definitions, right? So what is the algebraic part of this on the algebraic side? So this conjecture, as you can see in the study from the 70s. So I will also tell you a little bit about how far is the conjecture from being proven. So what do we have in the right chat? We have this, we have two posets. I mean, there are more posets, but we are going to focus only on these two. Actually, it's enough to look at one of them, but we will look at these two. So this SPG, this is called Brown's complex, and this is the poset with all non-trivial subgroups of G. Right, so this is a group. And the order relation is inclusive, right? So, and then this other poset APG, it is called something like Quillen's complex. And this here we have all elementary abelian subgroups of G, which are not trivial. The order relation is inclusive also, and so this is actually a subposet. Now this is elementary abelian subgroup. Okay, so out of this poset we can make a topological space, right? So we can do if P is poset. So what is this realization? We can take the simplicial complex where n simplices are the n chains in the poset. So this means that you have some objects in your poset, and each one of them is contained in the next, and this is an n simplex in your simplicial complex. This is the usual way to realize a poset. And probably many of you are familiar with this. I think. So what else? So this is a little bit of the topological side, and we need one more element. So given this G, we have also some subgroup here called OP sub G. This is subgroup of G, and is the largest subgroup normal in G. So this is normal in G. Is Pisa group? It could be trivial, right? Or it could be, I mean, anything, right? Between 1 and G. So, so what Quillen proved in this paper from the 70s, he realized the following. He realized that if the first thing he realized, I mean, he proved several things in this paper, but in particular, he proved that if G is finite group, let me write the hypothesis for once, all of them. E prime. So he proved this, that if this subgroup is not trivial, then this topological space is contractible, right? After the conjecture will be whether the other implication is true or not. But before that, let me give you a hint of, I mean, how Quillen proved this, because the proof is quite simple and it's very nice. So this is proof, like sketch. This is the way Quillen did it. So what did he do? So he did the following. He noticed that you have two posets, P and Q, and you have two maps of posets. So they preserve the order, right? The two orders. So the thing is that you can compare them. So if one of them is always smaller than the other one, so I mean that for every P in P, FP is smaller than GP, then these two maps, if we take the two realizations, P and Q, and we look at these two guys, the realization of F and that of G, then we have that these two are homotopy. Right? So with this little tool, he proved this implication. I mean, this is not the conjecture, but the suppose that this implication, because so imagine that we have this OPG, which is non-trivial, right? So what can we do? We are going to define some maps from SPG to SPG. Actually, three of them. We're going to see that, I mean, the first one is going to be the identity, the last one is going to be a constant map, and then we put something in the middle. So what can we do? We can send let's say every subgroup here, every non-trivial subgroup, we can send it to the identity. Then we can send it also to where? To HPOPG. Because OPG is normal and P-subgroup, then this is also a P-subgroup, right? This is the thing. This is the reason why this works. Let's call this, I don't know, R. So this is R, and then we can send it to OP of G. Okay, so this is, let's call it constant of H. So these are three maps of posets because they preserve the order. You can easily check it. And what happened that the H is always smaller than H times OPG, and this is always bigger than OPG. So this implied by this little result before, I mean on top, that the identity, representation of the identity is homotopy to be constant. Okay, so this implies that SPG is contract. Okay, so this is the known implication. And then in the same paper, Quillen conjectured that the reverse implication should be true. And actually he proved it in some cases. So Quillen conjecture, let me state it. So we want to prove that if SPG is contractible is because there is some non-trivial pizza group, right? So this is the, I mean, this talk is about this conjecture. And this thing, I mean, this argument here is called conic, or Quillen call it conic contraction. So let me tell you, I mean, just one example. So actually the conjecture is some kind of fixed point theorem, something like that. Because if this thing is contractible, we need to find something which is fixed under conjugation by G, right? Something which is normal. So let me, that is, this example here. This is S2, S4, where S4 is the symmetric on 4 letters. So this is, I mean, depending on which notation you like. And the prime is 2. Then if we look at all the non-trivial pizza groups, we really have this thing. So B is this client subgroup in the middle. And then we have some C2, some C4s, and some dihedral. So what this conic contraction does is something like, I mean, if this is the poset, and we have the normal thing in the middle. Here in this case, this is O2 S4. So that is something non-trivial, right? So the contraction is in 2 steps, right? Before, I mean, the first step, we multiply times the OP, so we go on top of this cone. And in the second part, we collapse everything into G, right? This is what's going on. This is the theorem, not the conjecture, of course. In this case, for instance, if we take, I don't know, for instance, this C2 here, this is already contained in V, so this one goes just to B. And if we take, for instance, this C4, then we multiply by B, we get to the D8, which is on top of B, and then we collapse. Okay, so the conjecture says that if actually we can, I mean, if SPG is contractible, it's because something like this is going on. There must be, the contraction must be conic contraction, because we are saying that OPG has to be non-trivial, right? So the geometric intuition is, I think, it's quite nice. I mean, now the thing is how to find this OPG, right? So then, let me go through some of the known results. So the idea of this talk is there is some, I mean, the best results so far is from Aschbacher and Smith from the 90s. And also in Quillen there are some results, but Aschbacher and Smith is the best. So what I have been developing this few years, I mean, this last year is like an alternative approach. I am reproving the known cases with the hope that I will be able to prove some of the unknown cases with these techniques. So my techniques, I think they are more geometric because I'm not a group theorist, so I need to use less group theory. So let me go through some of the known results. So let's see. Let's change color. Also, if you want to ask at any point, just interrupt me. That's fine. I'm happy with. So some known results. So for this, we are going to write which is the dimension of the largest elementary abelian pizza group. I mean, we look, I mean, whatever there is some CP or there is CP, CP, or, right? This is R1, R2, R3, and so on. We'll look at the largest elementary element. So I still need to tell you why I was into this APG instead of SPG. So I will do that in a minute. So some known results. So this is a general overview of what is known. So if R is equal to 0, 1, then this is trivial. Okay, because if R is equal to 0, then that is empty, the empty poset. And if R is equal to 1, it's just a tautology, because if R is equal to 1, there is one CP, and this guy is going to be normal if and only if OPG is non-trivial. I mean, this is. And now the next one is R equal to 2. So that means that this will improve this case. And how did he do it? So in this case, this is what? I should have said something. I mean, this is what I should have said before. So let me write it on top. This is always true, that this topological space has the same homotopy type as this one. Okay, so instead of looking at all the non-trivial Pisagro, we can just look at the all non-trivial elementary abelian Pisagro. I mean, I thought of giving you a sketch of the proof, but these are along the same lines as the other proof. Okay, so we can either work with the all Pisagros or just the non-elementary abelian. So the non-elementary abelian, I mean, they are nicer because all the rays below, they are very nice, right? Because whenever we have one of these CP, we know exactly what is below. So how would improve? I mean, we prove this. This is due to Quillen also on the same paper. So using this, and then if the rank is 2, then this is what? This is one-dimensional. Right? Because CP is a vertex, and CP times CP, a chain with CP is an edge. So this is one-dimensional. So if we assume that this is contractible, so a contractible one-dimensional complex must be a tree. And then G acts here by conjugation. And then there is a theorem of Serre that says that a group acting on a tree has a fixed point, right? There is 6 fixed point. And then this fixed point has to be normal, because this is conjugation action. So this proof is also very inspiring, because it gives you a hint that this is really a fixed point. So now also for R equal to 3, there is a recent proof by, let me see, this is from, I think, this year, or this paper of Quillen is from the 78. And this is Peterman. And then so they prove the next case, but I think they use the classification of the final simple. So this approach apparently doesn't go very well when you increase the rank these are. So then the solvable case, when G is soluble or solvable, let's say solvable, it was also proved by Quillen in the same paper. More things. G is solvable. They were proven by Alperin, I think in the 80s, because this is not published, but it was proved by Alperin, and then he used Coprine action results, and he used the classification of the final simple groups. Okay. I mean, it would be very nice to have a proof of this conjecture without the classification, of course, as everybody always wants to remove the classification from the results. And then the best result so far is from Aschbacher Smith. So what they do is they look at simple groups. And then from these simple groups, let me write the result. G, let me see. G doesn't have unitary component. Q. Okay, so the component, I mean, if I don't know how much in our group. Okay, so you look at you can look at, for every group, you can look at the simple groups that are like inside of your group, right? You look at something called the legend, and then you can look at how many simple groups you have inside your group. So what they prove is that if these groups inside, these simple groups inside your group, if any of them is the unitary group, okay, of type n with this condition, Q is -1 mod p, and the p has to be bigger than 5, then current conjecture false, okay? And this is due to Aschbacher Smith, and the GR is 93. Okay, some more stuff. Let me. So what I am going to do is reprove some of these results using this geometric idea that I will tell you in a few minutes. Yeah, today I think I am, when I give a talk, a live talk, I think I go quicker than this, so I have to remove some stuff. So there is also a nice result from Quillen, the same paper. And so let me recall a little bit the classification of the final simple group. So this one also uses classification, of course, because you have to look, you need to know what are the possible simple groups that appear inside your group G. So more or less, I mean, very sketchy. We have the alternating groups. I mean, these are the non-abelian final simple groups. Lie type. So these are like metric groups, and they are in non-defining characteristic, non-defining. Okay, for instance, it will be. Oh, I mean, not this group GL, because we need to take SL and then kill the center, but.
Antonio, can I ask a question?
Yeah.
So this Aschbacher Smith result, how general, like, what is the chance a group have this condition among like simple groups, for example, or like,
Yeah,
is it like most of the groups or not?
Yeah, so imagine, I mean, inside, I mean, these matrix groups, so they can be linear or symplectic, orthogonal, or unitary. So the proof works for all of them, but for the unitary case, when the Q is with this divisibility condition. So actually, it's like the best case. It's the worst case. When I go do some of the proof, you will see why it's so bad, because it's like in your metric group, you don't have enough room to do something. So,
Okay.
so in particular for unitary groups, in all this kind, the conjecture is not known yet. So if you take G equal to this unitary group, it's not known whether the conjecture is true.
Yeah. Okay, thank you. Thanks.
Thank you very much. And then lead type indefinite character, this will be something like GL, and then of course Q is E to the N. Okay, but to make the simple group, we need to, for instance, take the special and then take mod out by the center, something like that. Okay, and then we have the sporadic kind of simple groups. So also you can see that Aschbacher Smith, they prove it for p bigger than 5, because for smaller prime, there are a lot of exceptions to check for the sporadic, and especially for p equal to, I mean, it could be done, but there are many exceptions. So at some point, I hope somebody does it. My aim now is to prove the unitary case, but I am close and far so far. I will tell you a little bit more. And so there is a main difference here in between, I mean, between these two cases, the defining characteristic and the non-defining characteristic. So this is what I want to tell you. In the Lie type, in defining characteristic, what Quillen proved in the same paper, that this guy is homotopy to the tips building. And then this is a wedge of a sphere of the same dimension. So what can happen here? This L is the rank, the lead rank of, so the number of roots. So this is interesting to be compared to the non-defining characteristic, because here you can have, this L can be fixed. I mean, this is basically, you have matrices of size 10 times 10, then the lead rank will be probably 8. Right, so you fix the size of the matrices, this L will be fixed, so the sphere of the same dimension, but the P rank can go very, very high. If you take Q equal P to the N, then you can have this L fixed, but the rank of the P rank of G can go, I mean, it can be as big as you want. It will be something like, it depends on this M. If you take bigger power of M, it will go to infinity, as M goes to infinity. So the idea is that the dimension of the complex is fixed. SPG has fixed dimension, but the P rank goes as far as you want. And now on the contrary, for the Lie type in non-defining characteristic, the situation actually is expected to be to behave totally different, because what is expected actually is proven in many cases. What is expected in non-defining characteristics? So as Aschbacher and Smith, they introduce a property that we call it QDP, Quillen dimension property. And then they say that G has QDP if what? If the reduced homology of G, I mean, of the Quillen's complex, I mean, we could put here integral or rational coefficient, doesn't matter much, if this is non-zero. So this means, I mean, remember, I remind you that this R is the rank. So that means that if we look at the, also APG, the dimension of this guy is R minus 1. So it will, for these cases, for the Quillen dimension property, we look at APG. So we just look at the non-elementary abelian pizza group. And this complex will have potentially dimension R minus 1. Okay, it could be contractible or not. And what this property say is that actually APG has exactly that dimension. So homology is non-zero at the highest possible dimension where it could be non-zero. So this is really opposite to the cases for the defining characteristic, because the L is fixed and the rank can go as can be as big as you want, then all this homology will be 0 from the rank up to the L, and in the L we will have some non-zero homology. This is for defining, and for non-defining you really hope, and actually it's true that really on the maximal dimension where the homology cannot be 0 is going to be different from 0. And so what Aschbacher and Smith did is to prove this property for all these families of finite simple groups. For starting with the alternating, and then in the non-defining characteristics, so they treat the linear, the symplectic, orthogonal, some of the sporadics, and so on. Okay, and the unitary when the field of coefficient doesn't satisfy that condition. So what time is it? So I think I have been talking for half an hour. So let me. Okay, so. Sorry, so I mean, this paper for me are quite complicated because they use, I mean, you really need to know the classification very well. They do, as well as they do some kind of induction from some metric groups with other metric groups. So when I was reading this, what I try is to do some different approach. So let me, let me tell you about this geometric approach. To prove this QDP property. For families of finite simple groups. Yeah, so for me, this is easier than Aschbacher and Smith and Quillen's proof, but I guess for other people it will be harder. I don't know. So what is the idea? So let me go back to black. So the idea, we are given a group G, P a prime. Let's say that R is this rank, so the dimension of the largest elementary abelian subgroup. Yeah, actually we could take one of these elementary abelian subgroups. So imagine we take one of these. And we also know that OPG is 1. And then the question is whether this homology is non-zero. So we really want to build a homology class on this dimension. So what I do is a very constructive way of building these classes. So how do we start? I mean, G has to be one. We assume that G will be some kind of finite simple group in non-defining characteristic, okay? Because in defining characteristic, we know that this is actually not the case, so this cannot be true. So here's the idea. So we're going to build a sphere on this R minus 1 dimension. So the first thing to build one of this sphere is we need to build like the faces, okay? It's going to be a simplicial model of the sphere. So where we're going to find these faces, so we have this E. And if E is in G, right? So also we have oops, sorry. I meant I don't even mean that. I mean this. This is a sub-simplicial complex of. So let's build this face. So let me see. Let's do it. I think the best thing is to do one. We are going to build these faces as some barycentric subdivisions. For instance, remember that here we have, what are the guys here? These are the chains, right? So if, for example, if we take, imagine that this guy is generated by, so we are in R equal to 3. So we can look at this, and in APE, what do we have? So we have here on top, we have one guy. Okay, then here we have FP, we have many of them, and then in dimension 0, we have a lot of copies of FP, right? Something like this. And what? And somewhere here there are many copies, more than 3, right? But one of them will be A1, one of them will be E2, and some of this guy will be E3. So we can actually make a barycenter subdivision of a triangle like this. So I remind you that, I mean, this is generated by, but I'm going to omit the brackets. So it could be H, this is vertex, this is vertex. I mean, this is the usual barycenter subdivision actually. So this guy here will be what? It will be generated by E2, E3. This guy here will be generated by E1, E3, and this guy will be generated by E1, E2.
Do you mean E instead of H?
Yeah, you are right. This is E, sorry. This is an E. And I'm doing this. Yep. So I mean, and then what if, for instance, what if this H here? It will be E3 included in E2, E3, right? So this way we get something. I mean, this is barycentric subdivision of delta. So we can do this for every arc. So these are the pieces we want to glue. And now, how do we glue these guys? I mean, whenever we have this E of rank R, we have all these faces. And actually, because G acts by conjugation on E, then G also acts by conjugation on these faces. So the thing is, can we consider different faces and put them together to make a sphere? And the answer has to do with some group theory. For instance, in this case, let me improve the picture. So imagine we have the same small triangle here. So let me write it in the same order. So this was E1, this was E3, this was E2, right? And now imagine we find a guy called, let's call this C3, that centralizes, so it's in G, right? It's an element in G that centralizes E1 and E2, but doesn't normalize E3. So what happens if I conjugate this piece by this guy? So this H is going to be fixed. And then the E3 is going to move because it's not, because I'm assuming that this guy doesn't normalize. So I'm going to get another face similar to the first one, but with a common edge, right? So this guy here will be E3 conjugated by C3. And now, if we also have same situation, so C1 that fix this two guy, but doesn't normalize this guy, and then some C2 that fixes generated by 1 E3, but doesn't normalize. Then if, and also, I mean, there is one more condition. The thing is that because we are making new faces, so at some point we want that these faces, they go back and they glue together nicely. So actually we want this. That they commute. So that means that if you start with C1 and then you do C2, and so if you do C1 again, you don't get anything new. So with this condition, it's easy to check that actually the figure you get here is an octahedron. right? For instance, here we apply C3. To get this, we need to apply what? So this has to be, this is the element that fixes E1 and E3, so it has to be C2, right? And then, yeah, and then here we would apply C3 again. And so, and then because of this commutativity condition, you can check that actually this is octahedral, which is a sphere, right? So this is the, I mean, there is one more. So this is the approach I take to report this thing. So let me show it in. So it's building this Bilkent subdivision first, and then looking for this element. So now all the arguments, once we have this way of building a sphere, is how do we find these CIs, this element, right? And that's actually all the work. So let me write the theorem. So G finite group, P prime. This is the rank. We take an entire abelian of the maximal rank. And then if assume CI is in CG minus this, actually I will write here E, doesn't matter. Blah, blah, this is, we have these commutativity conditions. So then, I mean, this is what I draw before, but with symbol, right? Then what is different from zero, then there is some sphere in this homology, so this homology is non-zero. So once we have this, now the thing is, yeah, how to build this, how to find these guys. So in the rest of the talk, let me give you some hints. I mean, it's easy to do it for solvable groups, it can be done. Because a solvable group, you can look at the, actually it's more or less abelian, right? If you look at the fitting subgroup and, well, you have to apply some lemma and then look at the fitting subgroup and then take the Fratini quotient, but at the end you can get to something abelian. So in this abelian thing, the commutativity condition is for free. So this is, I mean, we are not going to go through all the details. In the solvable case, you cannot get it reduced to the abelian case. You will, at the end, this CI will be in some abelian part, but there will be also some part which is a simple P prime group. So here we really need to use classification to find CIs. And now let me show you how does this work in Lie type, right? In Lie type groups. Lie type groups is non-defining. I'm also alternating or symmetric. So let me make just a few examples and then it will be. Okay. So for instance, the easiest case is the alternative. So let's have a look at this case. I'm going to do it for the symmetric, and then for the alternative group, it works the same. So imagine we take G is equal to sigma n and some prime P. Then the rank is this, the floor of this M over P. And now what? So we need to choose an elementary abelian, and then we need to choose these EIs, and then we need to choose the CIs. And the idea here is the same idea as for metric groups. So we're going to think of these permutation matrices as, as permutation matrices. So they are n times n size. So we can take E1 to be this has order P. Then E2, what will be? So they will be P plus 1 up to P. And then this will be what I guess is this is right. So if you think of matrices, we are thinking of E1 will be here, then E2 will be here, and so on. It will be E2. If you think of permutation matrices, ER will be here, and then there is this is all of the same size, and then there is something which, I mean, because of the integral division, right? And so, and now let's think of the CI. CI has to centralize, for instance, C1. Let's think of C1 has to centralize this bit, but we don't want it to normalize the full thing. So this group E2 ER is generated by these block matrices. So if we want to centralize that, it's enough to take something which will live here, because every metric in this block will commute with all these other blocks. So it's enough to choose C1 on this block. And then if P is bigger than 3, then it's easy to see that there is actually on the first block of size P, the E1 will be, I think I will do E1 will look like something like this, right? So if we can take any matrix, permutation matrix in this block that doesn't normalize this guy, because then it centralizes all the other blocks and doesn't normalize this one. And this is true for, this is true for P bigger than 3. So for P bigger than 3, there is 6, C1, there will be permutation of P element that doesn't normalize this guy. But this is the idea. The idea is to take the joint blocks, and then the EI will be there, and then CI is just because of this joint block. We just need to look at one of the blocks. Yeah, so the idea for instance, one lead type, let's take now GLQ here prime. Yeah, this is the smallest integer such that QD minus 1 is 0 mod P. So this is the analogous argument to the symmetry group, but for general linear, okay? So let me see one thing here. So in this case, the R is again n modeled by this D. So again, the situation is similar. We split, this is times n. We take blocks of size D. And then at the end, there is some left over here. And we are going to proceed in the same way. So how do we do this? So now we have what? We have these are the automorphism of this field, right? So this is size QD minus 1, right? And then because these are vector space automorphism, we can map this to GLDQ. So this is one of the blocks, and then we can take this to the full thing. So here we can take some, let's call it x of order p, right? Because p divided p d minus 1. You have to think of this like the analogous argument for the general instead of the symmetric. Then they will go somewhere here. Let's call it y. And then we put it, I mean, there are several ways of putting, right? Depending on which I. We put it in the right block. We put identity, and here we put the y. So they will be the AIs. And then a small argument like before, so that to build the Cs, we need to look at one of these small blocks. So we need to avoid normalizing this y. And then if the only exception is, I mean, we need b bigger than 1, then there is ci gl dq minus normalizer of this element. And so again, because of these disjoint blocks, we can choose these CIs, and then we can build a sphere. So here there is already the condition of d being bigger than 1. And the unitary case has to do when this equal to 1, because if you think here, when this equal to 1, then the small blocks in the middle, they are of size 1. And then inside 1, everything is abelian, so you don't have room to do this non-normalizing thing. So the problem is when d is equal to 1. So we can solve, I mean, the counterpart to the unitary case is the special linear case. So the special linear case with d equal to 1, we know how to solve. So I'll show you how, and then the unknown thing is this thing, but for unitary matrices. Okay, so let me do this case. D equal to 1, and then there's condition that, well, this should be 1. Otherwise, I mean, this is not very problematic. But this is just to show why this unitary case is an exception. So this is known. I will show you how. So if we think of the approach like in the symmetric or the GL, it is not going to work because of this D condition, right? That D is equal to 1, so the blocks are of size 1, so you normalize because you are abelian there. So still we can solve it. Here the rank is minus 1, and minus 1. So how do we solve this case? So like follows. We choose first, we choose U in GL Q such that as order P. This is possible because P divided Q minus 1, okay? Because remember that D was the smallest exponent such that P divides QD minus 1. So we can choose like this. We take this U and we put it all along the diagonal, but in the first place that we put U to the 1 minus M. And we do this choice because we are in SL, so we need to have determinant equal to 1. So we keep moving this U to the 1 minus M. And we do this because the rank is, we just need M minus 1 guys like this, so we do this up to this guy. Okay, so all these guys together give us the elementary abelian we want. Another thing is the CIs, how to build these guys. As you see now, the approach still have the 1 times 1 blocks, but now the C1 we cannot choose them inside the blocks because they are of size 1. So, but still, that is in this case we can do this. I mean, you can say that these guys. So these guys are identity, and then we put a 1 here. C2 will be identity, and we put a 1 in the second row, last column. And it will be the last one. And then you can say that these guys, they commute, and they satisfy what we got before. So they centralize everything but the given. So here you can see the problem more or less, because in the unitary case, I mean, these matrices are not unitary. So, I mean, you can choose the form you want, and I mean to find unitary, but whenever form you choose, you will say something like, if you want to make this matrix unitary, you need to add maybe a -1 here or something like that, or start like this. And then you can check, and then they won't commute. So in the unitary case, this doesn't work because there is no room to make these guys commute. And actually, I check it by computer, and no such choice is possible for unless for small n and q. And I think what I am working now on, because I mean I think I have to substitute, because these conditions, I mean they give you some abelian group, right? The one generated by all the CIs will be abelian. But I think for the unitary case, this is what I am working on right now, is the condition is going to be of this type. So this is, so we actually need to introduce some break groups. So actually, for the unitary case, if things, I mean, I didn't finish. I had some linear algebra problems. I mean, linear algebra lemmas that I don't know how to put yet. But the thing is that here we are building spheres. And in this case, what I expect to obtain is not a sphere because of this lack of commutativity. The sphere will not get closed so quick. It will be one of these permutahedron. Right, so the sphere has two dm faces, and here the permutahedron have n factorial. Right, this is the permutahedron has one face for every permutation of the given order. Right, so I hope to finish the unitary case with these ideas of break group and stuff like that. Yeah, so yeah, I'm done. If you want to ask anything.
Okay, thank you very much, Antonio.
Yeah.
Any questions? Okay.
I can go back and forth.
Okay, I actually have okay, is there any questions?
Can you hear?
Who is speaking?
Do you hear me, or can I ask a question? Or?
Yes, we can hear you.
Is break relation CIs for the small intergroups? Do you know?
Can you repeat the question? I didn't really listen to it.
You said for the unitary group, you're going to find the CIs.
Mm-hmm.
Do you know if works for small ones?
Do I know if there's 6 for a small arc? Is that what you said?
Yeah, there's a.
Yeah, I found the CIs, but I have the candidate to I had the matrices, and they satisfy the break relation, but I still need to make I need some lemmas in linear algebra to prove like the how to say that the break permutation group is faithfully inside this permutation group, something like that. So I really need to stick close the permutahedron, something like that. But I had the CIs. I had the matrices. I don't know if I was
Okay, I have a follow-up question. So when you construct these spheres in the theorem or these permutahedron, how is it easy to show that they're not contractible really, or so which part is hardest, like constructing them or showing them they are not really contractible in the larger space?
the sphere?
Yes, in the theorem, for example. Yeah.
Yeah, the thing is that because the trick is that we are in top dimension, So we don't need to check that they are the boundary of anything. We just need, we have build a homology class with that, with this a cycle. And then because it's third dimension, they cannot be boundary of anything. So actually
oh, I see. Okay, so in the top dimension, right?
Yeah, this is all the time. We are using this Quillen dimension property is playing all the time with this. Otherwise, it will be much harder. For example, you could to do it for the defining characteristics to build this sphere in the dimension of the Lagrange, but then you actually you can, but then you will have to prove that they are not boundaries of anything. By non-defining, we are safe in that. Yeah.
Okay. And how did you come up with these the second relations in the at the bottom, the ones which give you these braid groups? How the first one is kind of natural, to start from a triangle and then reflect the triangles to glue a sphere. But what is the intuition for the second one? Like, I don't.
Yeah, the thing is that I did this computation, so I couldn't find if there is no CI that commute. That's for sure. But then, how did I get here? Yeah, actually, I think it was by trial and error. I tried to. I mean, these break groups are well known, and in the same way as these sphere are associated to the abelian group. I mean, I thought that the first easy non-commuting relation that could be possible, and this is the first that came up to my mind, and then some results on finite groups containing images of break groups. So I started looking for if I could find the CI satisfying this break relation, and I found them. And yeah, maybe there is something easier in between instead of taking the break group, but I don't know. I mean, this is what. I wish that would be something easier than the break group. But I don't know. So far, this is what I'm looking at. Yeah, I don't know if that was an answer, but something like that. I did it during the quarantine, so actually I was so obsessed with the problem that I lost track of all the papers I was looking for relation and stuff like that. Yeah, but I hope that I can finish this presentation. Yeah.
Okay, any other questions?
I guess I have a sort of silly off-topic question, but so have you looked at all at the dual version of the Quillen conjecture, where you consider instead of the poset of P subgroups, you look at the poset of index P subgroups, and ask about whether the O upper P of G is a proper subgroup. So this has been solved. Sorry?
Yeah, sorry.
Yeah, I'm just wondering, like, could your methods? So that's already been completed, I guess, using the classification. But could your methods be illuminating in that case? I'm not exactly sure how to. I'm not sure what the analogy of these. Well, I don't know. Have you thought about that at all, or?
No, I think at some point I read that it was solved.
Right.
So you say that it's also using the classification? Did you say nothing?
I'm sorry. Could you say that again?
Did you say that the proof for this dual version of Quillen's conjecture, it also uses the classification of the final simple groups?
I believe that's true. I think that's the case. Yes.
Yeah, I didn't look at the proof, so I don't really know if this can be applied. Yeah, that would be nice. I have no idea.
Okay.
Thank you.
Okay, any other questions from the audience? Okay, okay. Well, it seems like it's time to thank Antonio for the talk.
Thanks, Antonio.
Thank you.
Thank you.
Thank you.
Thank you to you guys. It was quite nice to hear this. How do we